Yeah, but we're not one problem.
So let's go over this moment of inertia stuff a bit, and then we'll finish that up. We started this a while back. So what you have there are a couple I shapes. They look like wide flange type beams. They're made this way on purpose. They're made this way so that they won't bend or flex a lot when they're loaded, okay? Because generally speaking, we want to avoid that in a beam. So the moment of inertia is a number that tells us how much stress will build up in the beam as it's loaded, as you're seeing there. So you look at the cross-section of the beam and calculate the moment of inertia about what's called the neutral axis, which runs through the centroid on the cross-section of the beam. And that number gives you some indication how much stress will build up in the beam as it flexes, as you're seeing right there, downward, okay? So that's what this number is. It's a bit abstract, it's not like a centroid where you can point at something at a location on a beam and say there's the centroid or something like that. It's not like that. It's more abstract. All right, so shapes that have a high moment of inertia, when you look at their centroidal axis, the material for the shape is placed a long distance away from the axis. Okay, that's what you try and do to create a shape that has a high moment of inertia, is get the material out away from the axis. And that's how you get the most moment of inertia for the least amount of material, which is what you want to do with a beam. Okay, so we see these T's and I shapes, most particularly I shapes, used around in different situations quite a bit. All right, now the basic definition there for a moment of inertia about the x-axis is y squared, which would be the distance times the area to which the distance measures from the axis. Then you add that up with an integral. So it's the integral of y squared dA. So that's the basic calculus definition. Now, quite often we don't deal so much in industry with calculus type stuff. We look at tables, and we have standard shapes that a lot of our beams and shapes are made out of, rectangles most particularly, also circles and sections of circles, triangles not so much, but it's possible. So what we do is we put composite shapes together, quite often out of rectangles. They might have some little fillet curves on them where the welding or casting is done to round that out, but normally they're kind of rectangles. So to calculate moment of inertia, we use something called the transfer axis theorem, which is you take the moment of inertia of a shape about its own centroid, then define the moment of inertia about an axis other than its own centroid. You then add a term of the area times the offset distance squared. And that's how you find the moment of inertia of a shape about an axis other than its own centroid. So we went through a little example like that. And what we did there was we found the moment of inertia of that T-beam. We took BH cubed over 12 for each of the rectangles that make it up. And then we took, to account for the fact we were taking the moment of inertia about the neutral axis here, which runs through the centroid of neither of the rectangles. We then took the area of each of the rectangles times that offset distance squared. Okay. And then we added that to the BH cubed over 12 term, and we got the moment of inertia for each of those rectangles about that neutral axis. Then we added those two together and got the total. So we okay with that so far? That's the basics of what we're doing. Now where this would relate is if we had a T-beam that's being loaded like that. So if we took that shape, that T shape, and loaded it as shown, we made it into a beam. So if you know the word extrude, you might use that if you're ever doing three-dimensional CAD. You kind of take a 2D shape and push it out and give it depth. So if we extruded that T shape and made it into a T-beam and then loaded it in the fashion that I'm showing, this number will tell you how much stress will build up in the beam on account of that loading. It will help you to do that. To do the full calcs on that, we go through strength of materials and we develop it in that class. But that's what this number is used for, to figure out how much stress will build up in a beam for a given load. Okay. All right. So that's what we got there. Looks like I lost a couple lines, but my beam. There we go. All right.
That's only for a rectangle shapes, right?
The beat.
To the 30/12.
Yes, that is for a rectangle.
The different I values going to be, the equations for I, is that on the blue sheet?
Yes, the 4 ones that I just showed you are on the blue sheet. So, and normally we're dealing with rectangles. We also have triangles and circles, and they're on there too. Okay. The transfer axis would apply to any shape. That theorem applies to any shape you're working with. Okay. All right, now that's just kind of done as a couple of equations. Let's get a little bit more organized. Let's take this rectangular beam. Let's say we got a trough cut out of the top. And let's go through the process you would go through to design the beam, or to figure out the moment of inertia of the beam about its own neutral axis. And we're going to find Ix and Iy. Okay. 690? It sounds about right. Is that 690?
Yeah.
Okay, so we're on 690. Now, what we're going to do here is we're going to find the moment of inertia of that shape about those axes. Those axes are placed at the neutral axis for the entire shape, which is 9.08 centimeters up from the bottom. Okay, so that's where the centroid is for the entire shape. So that's the line about which we'll calculate moment of inertia. Okay, now though that is the centroid for the entire shape, it is not the centroid for the shapes that make up the entire shape, because that's a composite beam. So those centroids are at those dots that I've just drawn in there. So we are going to have to use the transfer axis theorem for each of those shapes to get them onto the neutral axis. Okay. So there's our shape, and there's our 2 axes, our 2 neutral axes, you might say. So let's go ahead and get some of these numbers calculated. So again, I like to get everything calculated up first, so I just plug it into a table. That's how I'm going to approach this after I've run those numbers. So I'm going to find the areas of the triangles. They've got bases of 12 and heights of 6, so 1/2 12 times 6 is 36. Okay. Okay, now, and then I've got the height, or excuse me, the area of that rectangle would be 24, which is the base, 12 and 12, and then 15 high right there. So that's 24 by 15 is 360 centimeters squared. Okay, now what I also want are the offset distances, because what's happening here is that I'm going to find the moment of inertia about the neutral axis for this thing, which runs this way for the x neutral axis and that way for the y neutral axis. But these points, the centroids of the triangles that make up that shape and the centroid of the rectangle on that shape, are not on the x-axis, and the triangular ones are not on the y-axis. So I know I'm going to have to do the transfer axis theorem. So because of that, I want to get those distances, those offset distances, from those neutral axes to the centroids. Okay. So what I'm going to do there is I'm going to figure those distances up. So coming off the, well, let's start with the y-axis. Those ones are pretty straightforward, because all I'm doing there is just going 2/3 of the base of the triangles to either side of the y-axis. So the base of the triangles are 12. I'm coming from the acute vertex there, so it's 2/3 of the distance towards the right angle there. So in the base of 12, so 2/3 of 12 in both cases is 8. I've got +8 for the one on the right, -8 for the one on the left. Although those signs, as it turns out, are not that important, because it's we're going to do some squaring on this. We don't worry about the signs so much, okay, as it turns out. We're not going to have to deal with the transfer axis theorem for the large rectangle because the centroid of the rectangle is right on the y-neutral axis. They're equivalent, so there's a 0 offset there, so I don't need to worry about that one. Okay. Now, to get these offset distances to the two triangles and the large rectangle off the x-axis, I'm measuring in the y direction. So what I'm going to do here is figure out first, my neutral axis is 9.08 high. Then I got to figure out, and that's measured from the base of the rectangle here. Well, I want other measurements from the rectangle, so what I'm going to do is I'm going to measure, in this case, to the base of the triangles, and that'll be 15, that's given. So I'm going to go 15 from the base to the base of the triangle, plus a third of the height more. The height is 6, so a third of that is 2. So 15 plus 2 gets me 17. That's from the base of the rectangle up to the centroid of both of those triangles. So I'm going 15 plus a third of 6, which is 2. That gets me 17. Okay. Now the height of the neutral axis is 9.08, so if I subtract that off, what I'm going to get is that distance, and that's going to be 7.92. That is the distance from the neutral axis to that centroid, and that's 7.92 in both cases. Okay. You all okay with that? You got any questions on that? Yeah.
Is that 15 over 2?
Yeah, it is.
Okay.
Where, for the,
Yeah, sorry.
Right there?
Yeah.
Yeah, but that's for the rectangle.
I was just making sure.
So what I'm doing there, I'm finding a reference point that I can measure all those points from. I'm using the base of the rectangle because I know the neutral axis is 9.08. So from the base of the rectangle to the neutral axis is 9.08. From the base of the rectangle to the centroids of those two triangles is 17. So I know the difference is 7.92. Okay. Now I'll do the same thing for the rectangle from there to the neutral to the x neutral axis for the whole beam. What I'm doing there is I've got the distance up to the centroid of the rectangle. That's half of 15, so that's 7.5. Okay, because the rectangle itself is 15 centimeters high, so half of that would be 7.5. And then I want to know where the neutral axis is. Well, the neutral axis is at 9.08. So if I take 7.5 and subtract off 9.08, I get that distance that I'm showing there, which is negative 1.58. So that's the distance from the neutral axis to the centroid of the rectangle. It's a negative distance. So that that's going down, basically. Okay. Now, again, I don't get too worried about the signs on these because it's AD squared is the transfer axis piece, so that'll just square out anyway. Yeah.
Why is there a distance when that's the center of that is the center of the rectangle? Why is there a distance to it?
Because we're looking at the centers of two things. The neutral axis is at the centroid for the whole shape, which is the rectangle and the triangles.
It's not at the center of the rectangle?
No, it's not.
Okay.
The triangles are essentially pulling it up a little bit is what they're doing. Okay. And then we're going to the centroid of the rectangle. So there's a slight offset distance there. Okay. All right. So I'm just doing all this stuff just to get everything set up. So what I'm going to set up next is a table, and I'll just plug in everything into the table. All right. So we'll clean that up a little bit. There we go. Okay. So let's see what we got. Okay, we've got those three areas and the distances. So now I can work a table here. So what I've got is I've got, for part one, which is that triangle, I got I bar sub x. That's the moment of inertia of the shape of the triangle about its own centroid. So what that is bh cubed over 36. That's the moment of inertia formula for a triangle about its own centroid. So let's see what units I'm in here. I am in centimeters. So I'm going to go centimeters to the 4. So that's 12 for the base. The height is 6. So I'll cube that, and then I'll divide it by 36. So 6 cubed, is that 216 maybe? Maybe not. 6, is that 72 when I work that out? 72, okay, there we go. So that's 72. Now that's the moment of inertia of that triangle about its own centroidal axis right there. But I'm not taking the moment of inertia about that axis, I'm taking it about this axis. So I got to include that AD squared term, is what I got to do. So I got 12 by 6, so that area there is 36, I think, centimeters squared. We already calculated that. Then that distance we found also, and that is 9.08. So we good, 9.08? And then for our AD squared, we'll take 36, which is the area, times the 9.08 squared. And that will get us the offset term, the transfer axis part of this. Oh, I think, yeah, thank you. I busted that, right? Okay. Yeah, 9.0, thank you. Yeah, 7.92. Thanks. There we go. And that'll affect this term too. Sorry about that. There we go. All right, so we can take 36 times 7.92 squared. So that's 2258, near enough. And you can see how much bigger that is than the 72. So the total moment of inertia is the centroidal moment of inertia, 72, plus the 2258. It's 2330. So you can see how important those offset distances are. When you start taking flanges and things like that on beams and offsetting them quite a ways from the neutral axis, it has a huge effect on the moment of inertia. Okay. So that's 2330, I think, anyway. Yeah, that is. Okay, and we just repeat that process. The other triangle is the exact same thing from the neutral axis, the x neutral axis there. So bh cubed over 36 is 720, the area is 36, the offset is 7.92. The AD squared is 36 times 7.92 quantity squared, which is 2258. Add that to the 72, you get 2330. They're the exact same thing. Okay. Now the rectangle, its base is 24 and its height is 15. So 24 times 15 cubed over 12 is 6750. Okay, then we can get the area. We already got that. It's 360. The distance we already got is negative 1.58. So square the negative 1.58 and multiply it by the 360, you get 899. Now notice the negative goes inside the parentheses. So when you square, that negative goes away. The signs on these offsets for moment of inertia don't really matter because you square them. Okay.
Inside or outside?
Inside. They go inside the parentheses.
What about the fact that one of those triangles was negative 12?
Doesn't make any difference. Again, it's just distance. Whether
Okay.
the only time you get negatives on moment of inertia is if you use cutouts, if you start removing areas from shapes.
For area and that side.
Yeah, even though it's to the left, it still adds to the moment of inertia, so that negative squares out. Okay. So then we're gonna take 899 plus 6750, we get 76949, and we just add this stuff up, and we get the total moment of inertia, 12,309. Okay. So that's how that's figured out. So we want to be able to build a table and plug stuff into it, and then we'll figure out moment of inertia. That's the approach I like to use on this for these more complicated problems. So we got any questions on that?
The only thing that really changes for the y direction is the d value.
Yes, right. Yeah.
When we're calculating the 17 subtracted 9.08 to get this 7.92,
Right.
what are you calculating there again?
The 17 minus the 9.08, that's the difference between where our neutral axis is in the x direction and the centroid of the triangle. It's that offset distance. It's the d on the AD squared term. And when you calculate this stuff, you got to come from a reference line that you've got. And the reference line we have is the bottom of the rectangle. So the neutral axis is 9.08. The centroid of the triangle we figured out is 17.
Okay.
So that's the difference. Okay. All right. We good? So, all right. All right. All right. Now, how about I sub y? If we look at that first triangle, the one thing that changes is that we're looking at the y-axis now, this axis here. So what we call the base is parallel to the axis. So the base will be 6 on this. Okay, I define base as parallel to the axis. The height is now perpendicular to the axis, so that's 12 cubed, and then over 12. Okay, or not 12, 36. So that's 6 times 12 cubed over 36. When we did about the x-axis, it was 12 times 6 cubed over 36. We're going about the y-axis, so it's 6 times 12 cubed over 36, which I think is 288, be my guess. Okay. Okay, the area is was 36, and it still is, no change there. The offset distance is measured from the y-axis now, so it's this distance right there. It's 8, I think. So 36 times 8 squared would get us the AD squared term. So whatever 36 times 64 is. Yeah, 2048. And then we can take 288 and add 2048 to it.
I think that's 2304.
Did I bust that? Okay. How did I do that? So 64 times 36. Yeah. I don't know how. But there we go. Thanks. So there we go. So that's 2304. Then we'll add the 288 to it. And we'll get 2592 for the total. So if you just are looking at the moment of inertia of that triangle about the y-axis there, it's 2594. And the units on that are centimeters to the 4. Okay. So once you finish that one off, have we got any questions on that? Okay. So we can get the rest of that knocked out. there's kind of a trick answer for that offset for the rectangle. It's too easy.
Yes. It's like how far the center is away from the center of just the graph. Is the center.
Yeah, I get another 2, 5, 9, 4, and then another BHQ number 12. What's the offset for the rectangle? Yeah, it ain't much, it's 0. See, what's happening there for the offset for the rectangle is, we're on that purple line for the neutral axis, and the rectangle, it's centroid, it's just right there. It's right on the purple line, see? So the offset is 0 for that, okay?
I think it's 2592.
Really, we're having problems here, aren't we? Sorry. There we go. There we go. And then what do we got? Y'all doing okay with that one? The rectangle to the right is identical, except there's a negative. Well, this is actually -8 here, not that it really matters, but it was. And then the rectangle on the right has a +8. And then you're doing the BHQ number 36. Okay, so we got any questions on this one? So, as I've mentioned, this is kind of a more abstract kind of thing than a centroid. I can point at a line at a point and say that's the centroid, but I can't do that for the moment of inertia. For the moment of inertia, it's a more abstract concept. And what this is, it's how well the beam would resist bending about a given axis. It's kind of about how much stress would build up in the beam in a given direction. So if I have a beam like that, and I'm supporting it, something like that, and then I load that beam, when I load it down, I use I sub x, and that tells me, or is part of the equation, I should say, that will tell me how much stress will build up in that beam. Okay, so for that load there, I use I sub x. So maybe it'd be better if I showed that on the other page, because for this loading, this is what I would use the number I just calculated there, I sub y, for a loading like that from the side, because what's happening then is you're bending about a y-axis like that, okay, on the cross section.
Would that be like, if you were mounting something at an angle, that be
Possibly. You know, the two things I can think about that, one would be wind loading on a wall, the other would be an earthquake where you've got what are called lateral loads. Okay, that's probably the more common places you'd see something like that. Okay, now the other number is I sub x, and that's going the other direction. So what that is it's the same beam, of course, because that's the beam we've got. So we've got this rectangle with a little trough cut out of it, maybe for drainage or something like that on a roof, I don't know. But so we've got something like that. And then we connect the dots and we get our little poorly done sketch. There we go, and we take this stuff out. I guess we got away with that. Then we do that. And like that. Then we put it down, come over here, drop that. Okay, so I sub x is for a loading like that, the typical downward loads that you get on a structure. That's what I sub x is, okay? Now there is kind of a difference in nomenclature I want to call out here. When you talk about the centroids, the letter refers to the direction you measure. So x bar is measured in the x direction, y bar is measured in the y direction. But I sub x is about the x-axis, okay? They're different. The subscripts mean slightly different things, so keep that straight. So like x bar, when you look at that, is measured actually off the y-axis in the x direction is what x bar is. You're saying here's the centroid in the x direction. That's how far over you measure. But I sub x is actually the offsets are measured in the y direction off the x-axis. So they're kind of the reverse of each other in how they're notated. Okay, so just be aware of that. All right, they're called out differently. That's what I mean by that.
So that's why it's 7.92 for IX instead of 8.
Yes.
Okay.
Exactly right, and it's a little confusing sometimes because centroid, you're using a y distance for an x moment of inertia. For centroids, it's not that way. For centroids, if you're measuring the x direction, you call it out as x bar. So they're a little bit different in how they're notated. Okay, so just be aware of that. The centroid notation refers to the direction you measure. So x bar is in the x direction, y bar is in the y direction. But moment of inertia refers to the axis you're using, you're calculating that about, okay? All right, so that's just a run through moment of inertia. And this is a little bit, it's a shape property. This is area moment of inertia. You'll do mass moment of inertia in dynamics and physics. And unfortunately, we don't use this fully. We just kind of show you what it is. You'll use this if you take strength materials. We'll use this, and we do beam stresses, bending stress, and stuff like that. Okay. So that's mostly for mechanical, civil, CEM types. You know, those in the chemical biofields will probably won't get to that. I don't think you have to take that. I don't think anyway. All right. All right, so that's a little bit on that. Let's see. So we got any questions on that? Running those calcs? Okay. Let's see. Let's have a look at a couple of things here. There were just a couple things that came up on the homework, so I thought I'd go through a couple of them. This one seemed to cause people a little bit of trouble, so why don't we just run through this. These are those frame and machine problems that I just handed back here in class. I haven't graded them online yet, but I'll get on that. It's on the list of stuff to do. I always like to grade the in-class stuff because they're only here certain times. I can only return it at certain times. So that's why I do it that way. Let's see. All right, now this one, so what we do here, we're going to start on the right and work our way over is how this will work. So what you would do on this problem here is you would start by figuring out that pulley there, the 48 pounds, goes right on the pin at the pulley. And then I'd see that I have a two-force member there, EH. So that's some of the stuff that I would start with. And then I would draw the exploded view. So what I would do is I would start here on the right-hand side and work my way over to dx. So here I would go sum of m about point I. I'd set that equal to 0. And I'd have that cosine 20.78, and I'd multiply that. Oops, that's cosine 30, isn't it? Cosine 30 times 20.78 pounds, and then that would be times 10 inches. And then I'll look at that, and I'll notice that's going clockwise, so that gets a minus. And then I would add 4 times whatever FEH is. And that would be, as I have assumed there, counterclockwise, so that would be positive. Okay. So what that's going to get me is FEH, and I think that's 45 pounds, is that right? Okay, so that gets me to 45, so that now becomes a known. So now I'll come down to DF, and I'll take moments about F, and I'll set that equal to 0. And what I've got is the 45 pounds times 4. Now that's clockwise, so I'll put a negative on that. And then I'm going to get one of them that I want, and that'll be plus 9 dx. So f dx. So I can solve for f dx, and that's 180 divided by 9, so that's 20 pounds. Now notice that I turned EH around. It was acting to the left on GHI. And now it's acting to the right on DF, and I'm solving for DX. So it's going to the left here. It's 20, but that means it's going to the right here. So you do have to remember to turn this stuff around, okay? Now the sum of MC equation was the one that was a little bit involved here, so let's have a look at that. Sum of MC is 0. And what do we got? We've got 8 times dy, and that looks as I have it drawn. That's going to go around clockwise, right? So that'll be minus 8 times f dy. That's this one. Then I've got 20 pounds times 9, so that'll be minus 20 pounds times 9 inches. That's dx. And then I've got all those 48s up there. There's going to be 3 terms that involve 48. The first one will just be simple, and that's minus 48 pounds times 2 inches. That's the first one. That's this one. Now, the one angled at 20 degrees, there's two terms I have to pick up there. I'm going to have plus, and that'll be cosine 20 times 48. That'll get me the x component of that. That's this one right there. And that's going to be times 9 and 7 makes 16 inches. And that'll be positive because that's going to go counterclockwise. But then I'm also going to have the x component of the 48. So that's going to be sine 20 times 48 pounds. And that'll have a 2-inch moment arm. Now that's going to come around clockwise, so that gets a minus. Okay. So I'm going to have 8 times f dy is going to be all that other stuff, okay? Okay, so that's what went on there. I think some of you might have a sign error on that. It looks like we're going to get, what, 180 plus 96 minus whatever cosine 20 times 48 times 16 is. Cosine times 48 times 16, 722. And then plus whatever sine of 20 is, times 48 times 2. It's 33. So I think I'm okay with those numbers. So when I go ahead and do that, I'll get, 722 minus 180 minus 96. Minus 33, it's 413 is what I get. Divide that by 8, that's 51.6. And that's actually going to be a negative. So instead of acting the direction I assumed, which was down, it actually acts up. So that was that one. I think there might have been some sign errors on that. We got any questions on that? We are. Okay. Now the other one that might have given people some trouble was which one was it? Yeah, it was this one. So the first thing to figure out on that is that the tension is 600 newtons. Okay? So that's the first thing to understand there. And that's because you're holding up the 1200 newtons down there, and so if you draw a free body diagram of that pulley, you got 1200 up, and you got these two tensions going up. So they're going to be 600 to balance the 1200 down. And then that 600 will work its way around. Okay, so that's going to be all over the place, that's 600, because what we're going to have then is, if we look at what's going on there at E, we've got this 600 down, we have another 600 down for this one, and then that one pulls that way, so that'll be 600. So there's 3 of them right there. That's 600. And both of these are 600. Okay, so we have to account for all of those. I'm taking the first one, which is directly connected to E, and then I've got the 2 on the pulley, which both move to E. They're tension, so they pull, both of them. That's going to pull and that's gonna pull. So I can put these 600 Newton forces right at the pins is what I can do, like that, okay? So once I've got those, my free body diagram looks something like that. Okay, so then I just kind of work through this. I'm going to start at that flat one because I've got 4 unknowns on both of these, but I can work with a flat number like I've got from B to D to E, I think it is there. So I can just take moments about B and set that equal to 0. And what do I got? I've got my unknown dy times 0.9. And then I've got the 2 600ths times 1.6. Well, that'll be minus because it's clockwise, 1200 newtons times 1.6 meters, okay? Like that. So that should get me the 2133 for FDY. So 1200 times 1.6 divided by 0.9. 2133. Okay. Then I moved down to the lower one. I found that this was up at 2133, so that means this one's down at 2133. Okay, you got to remember to turn them around. And then I can take moments about A and solve for dx. Okay. So I'll go sum of MA equals 0. And that's going to be, I've got a lot of stuff to do here. So I've got minus 600 newtons times 0.74 meters. Okay. And I got plus 600 newtons times 0.555 meters. Then I've got minus 2133 times 0.9 meters. And then plus 0.675 f dx. Okay. So the first one I've got is this times 0.74, that's clockwise, so it's minus. Then I've got plus this one times its moment arm of 0.555. That's plus because it's counterclockwise here. And I've got this one here, which is the 2133 times 0.9 clockwise. And then one more, the dx times 0.675 counterclockwise positive. Okay. That's how that one goes. We got any questions on that? Okay. All right. So that's just a little bit of run through that for what I just turned back. Okay. All right, why don't we take a break here if there aren't any questions? So let's start up around 4, I guess. Or a little bit after 4. Yeah, around 4, we'll start up at 4.